Hi all, this is Mr. Yeager for chemistry, and we are on to our last part of this acid-base unit, which we're looking at titrations. And so titrations are a neat process that a lot of students do actually really get into. It's definitely kind of one of those signature chemistry labs where we are mixing an acid base together, and there's a color change, and it should come out very, very nicely in terms of, you know, the actual quantities that we're expecting with a lot of things. So what is a titration itself? It is an analytical method to determine the unknown concentration of an acid and base using a known concentration of an acid or base. Obviously, if we're trying to find the unknown concentration of an acid, I need to use a known concentration of a base and vice versa. But there is, while we are being very specific, saying this is for acids and bases, this is something that can be done for any sort of chemical reaction if you know the outcome that you're expecting and you have some way to know when there's an outcome, okay? But since we're focusing strictly on acids and bases, we are only going to be doing neutralization reactions with this, all right? An acid is going to react with a base. We will know one of the two concentrations, and based on how much we need, the amount that we need to the volume we need to neutralize it, we can calculate the concentration of the unknown, okay? So before that, we've mentioned these before, indicators, okay? Back in, all the way at the very, very beginning, when we were talking about properties and terms, I mentioned a couple indicators like phenolphthalein, pH paper is, or not pH paper, sorry, litmus paper is an indicator. We also have cabbage juice. There's lots of indicators out there. But an indicator is a chemical that changes color based on the pH of the solution. All right? It changes based on the pH of the solution. I don't know how often I have to talk to students or I get answers on tests that say, you know, my question is, what's an indicator? And somebody says, something that changes color. All right? That is nowhere near sufficient of what an indicator is actually doing. All right? It's more about the fact that it will change color. That's true. Why does it change color? It changes color because you're altering the pH of the solution, and at certain pHs it'll be one color, at other pHs it's going to be another color. The most popular one that we use in chemistry labs is phenolphthalein. High school chemistry labs is phenolphthalein. There are a number of other indicators out there. There's many, 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 many of them. Okay, I do use one called methylene blue in a reaction. We saw that actually in the equilibrium problem or equilibrium video that we saw. They used methylene blue. All right, so there's lots of different ones that change particular colors based on the pH. We like to use phenolphthalein because it changes close to a pH of 7. All right, it does it very, very closely to 7, and it changes that vibrant pink color. You know, some people say magenta color when you make it a base. So this is phenolphthalein when it's in a basic solution. Phenolphthalein in an acidic solution is completely clear. Okay, it's completely clear. So that is something that works out very, very nicely, obviously, too, where we can get that very nice color. Usually, though, when you're already that pink color, you're well above 7. So when we try to do these problems, you actually want just barely any pink showing up in it. So barely, where it almost still looks clear, but it's very close to pink. Oh, sorry, sorry. It's very close to clear, but with a pink hue, as we say, very much getting into our colors. So if you actually get to my site and want to see the titration process, here's a good video off of YouTube from my particular university. Sorry, that was a great plug on them. All right, but there they are. And then, but that'll be something, again, watch the video for. Obviously in class I can kind of go through it step by step a little bit more. For the titration math, our last equation, okay? And again, all the letters in parentheses should be subscripts. So if I rewrite this, it's NBMAVA equals NAMB. It can be capital or lower uppercase B, it doesn't matter. VB, okay? This is our formula for titrations, where we can then identify the unknown concentration or volume that we'll need with it, okay? So what are all these things? I'm actually going to skip the N's at first. M's are the molarities of the acids and bases. Okay? The V's are the volumes of acids and bases. Those alone, if I take out the N's, it looks like the dilution formula. Obviously, there's a lot of similarity with this being the dilution formula. Okay? We are trying to make sure the moles of acid and base are equal in the end. That's really what we're playing around with, is that the moles of acid and base are equal. That would mean we have a neutral reaction because I have equal numbers of H plus and equal numbers of OH minus forming water. But because it's a reaction between two different chemicals, I need to include these N's. I'll rewrite it over here. Na and Nb, and you can see that they are on opposite sides of where the molarity and volume of that particular chemical, acid or base, are. We actually switch them. Na and Nb are the coefficient for the acid and base in the neutralization reaction. I just realized I spelled neutralization wrong. Neutralization, okay? Sorry about that, that's Ti. So neutralization reaction. We have to do that because we gotta, if we're having equal number of moles and the acid provides more moles of H plus than the sodium hydroxide does or the base does, we have to balance the two of those things out so the overall moles is the same. So again, that's using basically a mole ratio calculation with it. Okay? So let's go ahead and jump straight to a problem with that instead of going to something else so we can see this. All right? So let's say I have this problem right here, and we're going to see how this comes into play right away. What is the molarity of phosphoric acid if 15 milliliters of the solution is neutralized by 38.5 milliliters of 0.15 molar NaOH? All right, first step, I need a neutralization reaction. So phosphoric acid, not hydrophosphoric. Phosphoric acid is H3PO4. Okay, that will react with NaOH, and as we learned from prior videos and prior practice, this will form water, HOH. I said I like to do that with acids and bases, and then NaPO4. Na is plus 1, PO4 is minus 3, so this is Na3PO4. All right, so I write my neutralization reaction, always water and a salt produced. I balance. I have 3 hydrogens. Again, I'm only looking at this first hydrogen. There's 1, so I'm going to put 3 there. I have 1 PO4, 1 PO4, 1 Na, 3 Na, so I need 3 OHs, 3 OHs. I am good to go. All right, so there we go again. So that's everything we have done before. We've written a neutralization reaction. Now what I'm going to do is I'm going to use my formula. I need to figure out again what I have and what I'm going towards, so I'll write that out too. But NBMAVA equals NAMBVB. So again, M and V go together. The N has to switch sides with again, acids and bases. So let's write down what I have. Again, I've seen that a little bit at the end here where some students are going, I'm getting lost in my problems, I don't know which one's which. Let's write down what I have. It says, what is the molarity of phosphoric acid? So right there, the question is, I'm solving for Ma. If 15 milliliters of the solution, that's the phosphoric acid solution, 15 milliliters of it, is neutralized by 38.5 milliliters of 0.15 molar. Whenever you see an of, these two things are together. And that's of NaOH. So my MB is 0.15. My VB is 38.5 milliliters. Now what about Na and Nb? Na is the coefficient in front of the acid. I have none, so that's 1. Nb is the coefficient in front of the base. That's 3. So therefore, I have all of the numbers I need for this, and I can go ahead and start plugging in and solving. So this would be 3 times the molarity of the acid, I don't know, times the volume of acid, 15, equals 1 times, 0.15, I want to make sure I have the right number, it looks like 15 over there, times 38.5 milliliters. As long as the units for volume are the same, we can leave it like that. We don't need to convert it. But if we do this, we get 1 times 0.15 times 38.5. That equals 5.775 on this side. That equals 45 MA. I divide the 45. MA is going to equal 0.1. I have 2, yep, it's only going to be 2.13 molar. It's 2 sig figs because I have 0.15 as the least number of sig figs. So 0.13 molar is my concentration of acid. All right? And if we watch the process, what that would mean is I probably would have, what would happen is in a flask, I would put 15 milliliters of the acid, 15 milliliters of this sulfuric acid or phosphoric acid. All right? And what should happen is I can put a couple drops of the indicator on in. And then what would go on here is I would start adding sodium hydroxide. And I would know that the sodium hydroxide is 0.15. We've made that. What would happen is after 38.5 milliliters have been added, the indicator would change color. And that's where I know the reaction is over and I should stop. It took 38.5 milliliters of base to neutralize all the 15 milliliters of the acid. Again, think about it. Why would it take so much more base than acid? H3PO4 has 3 hydrogens on it, so it has to be able to neutralize all of those hydrogens. Okay? But that's where we basically create all this. I'll do one more. Okay? For the second one here, it says I have how many milliliters of 0.45 molar hydrochloric acid must be added to 25 milliliters of 1 molar potassium hydroxide to make a neutral solution. So I have HCl plus KOH will produce HOH, water, and the salt, KCl. Well, that's +1 and that's -1, so this is already all balanced. So if I write out what I have my Ma right here, 0.45 molar hydrochloric acid, and these are two things together, and this is the molarity of the base, 1, and the volume of the base, 25. I want to figure out the volume of the acid, and Na is equal to 1, and B is also equal to 1. So for this one, we can kind of ignore those. I mean, I'll still put them in the problem. It's 1 times 0.45 times VA will equal 1 times 1 times 25. So in the end, it's just 25 divided by 0.45. I'm going to need a volume of 56 milliliters of acid in the end. And that's titration calculations. Nothing too special with them. Okay? I mean, again, very similar to dilution, except we actually have a conversion. It's sort of similar to solution stoichiometry. That's really what it's very similar to in the end, too. Okay? All right? So, going back to the slides. That's all the math. All we have to look at now are these things called titration curves. All right, so what we're going to be doing here is we could try to create a titration curve if we have some good equipment with this, where you can kind of see if we would need conductivity testers that would actually help us with this, and pH readers to make sure that we are reaching particular pHs at particular times. All right, but what this is showing you, excuse me, these curves are showing you when the equilibrium point is occurring. We call it the equivalence point. When does the moles of acid equal the moles of base? And there are a couple different shapes based on what types of acids and bases you'd use. So the first two here I have is basically a strong acid being titrated by a strong base. When I say being titrated means what am I adding to it? I'm adding a base to it. So the acid is there and I'm titrating with a base. So the base is being added. You can see both these curves look very similar. What we see, this is for a strong acid and a strong base. Just they're going to opposite directions because which one you're starting with. What this is showing you at the beginning is because it's a strong acid, we have a low pH. The pH is below 7. Here's 7 right there. And it'll stay that way for a while because if I add just a little bit of base, it'll neutralize some of the acid, but what's still majority there? Acid. The base just turns into water, but the majority of it is still acid. The pH drops a little bit because essentially when they react, you're forming more water, and so what's happening to the concentration of the acid? It is ever so slightly decreasing. So again, the pH doesn't really change too much, But then what happens is when you get really close to the point, like you can see right here, really, really close, where you're going, I only have a little bit of acid left. This is mostly water now with a little bit of acid. Well, actually, I mean, I guess there's still a decent amount of acid. But when you start switching, it'll immediately flip over to the other side. And at the end here, this is where now you've added additional base. This is adding too much base. Okay? You've gone too far. But the point on that line where you have the straight line kind of going down along it, this is what would be called the equivalence point, and this is the point where the moles of acid equals the moles of base. And again, if that's the case with a strong acid and strong base, the pH is going to be at 7. And that's because we should have only water and salt in it. And again, the salt might make it kind of go up or down a little bit. Salts do obviously affect pH minor, but that can cause obviously being a little bit different. The one on the right, same exact deal, but you're now adding an acid to the base, a strong acid to a strong base. So again, you can see those pictures. It's very much an S-shaped curved, okay, is basically what we say. And you're going to see all of them are generally S-shaped. It's just where does that start? And for a strong acid or strong base, it starts really high or really low, and then there's a steep change. Sorry, I shut the whole page up. A steep change when you're changing from acid to base, when it passes through the equivalence point. Now, if I have basically, this is weak acid with a strong base and a weak base with a strong acid. All right, again, I have the acid and then I'm adding the base to it, so the weak acid. For this, for the weak acids and bases, you start a little bit higher on the pH scale. Not at 7, just a little bit below it, but not down at 2. You can see I have the other line showing where the strong acid would show up. Same thing for the weak base. What we will see here is this little line as we go across will be a little bit longer in some ways. All right, you'll see a little bit of resistance for even that strong acid. It doesn't immediately make it a low pH. The strong base doesn't make it a really high pH right away. That's because when you are adding a strong acid, or sorry, a strong base to a weak acid or vice versa, you will get the conjugate acid and the conjugate base of that weak acid. And that conjugate base is actually kind of strong and can actually continue to try to react with it some. But we get that conjugate acid as well. So that will hold the area in the pH zone for a little bit longer. We call that a buffer. Okay? A buffer zone, where again that conjugate acid and conjugate base forming is preventing it from continuing to move that quickly up. It is altering the pH ever so slightly, and it is obviously affecting how much H plus can get into, or OH minus can get into solution. Okay? So you can see that that's one big point to notice. Obviously, more shallow curves, okay? They obviously start up higher. The other thing too, the equivalence point will occur a little bit above or a little bit below 7 based on whether you're adding a base or an acid. It's depending on what you are adding. So you can see with the strong base, the equivalence point will be at basically around, I would say, basically 9. So we are already in a basic solution because, again, there's that conjugate base present from converting it already. Same thing, the conjugate acid is already present some, and then obviously add more strong acid, it'll drop it really, really fast. Okay? So that's where we're getting with those things. I think I have, the only one I'm trying to show here, you can see all the same curves, is what if I have a weak base and a weak acid? You can see how shallow that one is. Again, weaker basically means it's not going to change as quickly. We should basically see that they do run into around 7 being the equilibrium point for them, but you can see how shallow that is because, again, they're not reacting very quickly. They're not neutralizing each other very well because their pHs are already pretty close. Okay? So those are all the shapes we need to be able to recognize. And all I'm asking is if I show you one of these, you can go, oh, this is a strong acid being titrated by a weak base. This is a strong base being titrated by a weak acid, or sorry, strong acid. And what shapes do they all make? Okay. So the hammer equivalence point one more time. Equivalence point is the pH when the moles of acid and moles of base are equal. That's what we pay attention to pick out our indicator. And then this hammer is kind of each of the situations. When a strong acid and base go together, we get an equivalence point at 7. When I have a strong acid and a weak base, the equivalence point will be less than 7. When I have a weak acid and a strong base, the equivalence point will be at greater than 7. When I have a weak acid and a weak base, the equivalence point will be at 7. All right? So that's something else to point out. The last thing, even though I don't think I'll be actually giving any of these out, but this is something just to see as well, to extend it. If you have a polyprotic acid, what do you basically notice about a polyprotic acid titration curve? Well, there are two steep points here where the pH is changing significantly. This is because each of these points represents when one of the hydrogens is being released. So if this is like H2SO4, what would happen is this is showing when one of those hydrogens has been completely eliminated from every single sulfuric acid molecule. So that's where every single sulfuric acid molecule is now gone, and I have HSO4, which is still acidic, which is why we stay down below, and we haven't jumped all the way. But then what happens is when I keep on adding more of the base, all of those will finally change into SO4 2-, and we get our second equivalence curve. So this is what happens if we had a triprotic acid, one with 3, I should see essentially 1, 2, and a third curve as well when all of them are released. All right, and that third one could occur at a high pH because it might be it might be at that point a weak base and be on that other side of the pH scale. Okay, but I think that's basically it. So we got titrations. It's a great process. Hopefully you get to do it in the lab if you're not in my class. But obviously if you are in my class, we will take care of this. A very neat technique to try to find the molarity of an unknown acid or base. And we use that formula, the titration formula, and we can then create possibly titration curves. But again, we're mainly just analyzing them. All right. Thank you very much.